Hey everyone, how are we doing? Getting started here. Sorry about that, Madison. Was doing a few emails right there, getting everything situated. Had to deal with some stuff. It's a Monday. It's a Monday. How's everyone doing? Hey Kayla, how are you doing? Hey Madison, hey Ashley, hey Tiffany, hey Caroline. We're gonna get started here. Let me get those notes posted. I need to put together all the notes. We're gonna wake up Mewbot. We are streaming, right? Tell me if we're streaming. It's a Bones Day. Feels like a no Bones Day to me. Feels like the world just exploded. I should have done it all on one sheet last night. We got so many sheets of stuff. Let's go right here and start putting everything all on one sheet. I felt that one, I know, right? I'm dealing with stuff. I hate dealing with stuff. Stuff. I'm dealing with the not fun part of my job, if you know what that means. The not fun part of Brian's job, he had to deal with a little bit right there, and it's a bummer. Things happen. I'm getting all the notes collaborated right here. Did you have a part of your job that you don't like, and it's the not fun part of your job, and you have to deal with it sometimes, and you're like, okay, sometimes I just have to do this not fun thing. Thank you so much. I appreciate that. It's rare. I don't have to deal with the not fun part of my job that much, but it looks like I'll be dealing with it over the next few days. The not fun part job. Not fun part. People. This is funny. I could agree. It's just sometimes people make errors in judgment, and that judgment error can impact them and others. And then we have to do the not fun parts of doing stuff. I'm getting the notes. I'm currently situating the notes right here. I won't be able to upload this yet because I don't have access to the... I have to... So I'm putting all the notes that we did last night on one sheet. And then we're going to reopen the quiz here. I am a paralegal. I know all about errors in judgment. Yeah. And if you ever... Let me just say this. Like, if you ever see something happening in, like, a group me or anything like that, if you ever... Now someone's wondering, what's Ryan talking about? If you ever see something happening in a group me, please inform, like if something happens that is a violation of the UT Honor Code, please inform people of that. Please, go to your instructor and say, I don't feel good about what's going on in this group me. People are maybe sharing things they shouldn't share. Like if you witness something, you're supposed to report it. I know that's a lot to go out on the line and say like, hey, you need to report this. Because you're kind of sticking your neck out there and being like, hey, there's a problem going on here. And then someone could be like, hey, that person told on us. Because, it might come back, especially if it goes to student conduct or something. But if you see things going on in a group me that you're like, ooh, that shouldn't be happening, you're supposed to. And like once I said again, I know it might be to be like, oh, I don't want to be the one who says it. Like, I'm just going to ignore that. I'm just going to leave this group me. I mean, that might be a good idea, too. Just leave the group me. I'll do Pearson and Spearman. Okay, we just got to Pearson and Spearman. Yeah, I know, right? Dealing with thing in the background. Not saying it's cheating, yeah. Yeah. Dealing with, and a lot of it comes from, let me save this before I forget to save it. And then we'll open the proctorial and then we'll get serious here. Put these notes. Exam 2 review night notes. Yeah, just it makes, so I've got the 13 sets of notes right here, put it all onto the thing, all the notes from last night, all the notes, is that what are people's thoughts on group me's? Like, I realize they can help people, but I swear, maybe I'm wrong. We used different things. We had chatting things. What do you think, Ashley? Is there cheating that goes on in group me's, sharing of stuff that shouldn't be shared in group me's? What do you see, Ashley, with that right there? Like, what do you see with those things right there? What are people's thoughts on that? What are people's thoughts on that kind of stuff right there? Mostly homework answers, yeah. And you think of the stuff I work on, yeah, like it's different. People are sharing projects. That's a major issue. I think they're helpful, but some people push the lines. Exactly. Yeah. Some people are going to share projects and where you're going into like some major, or share some like previous students' work from previous semesters and be like, hey, here's my friend's project from last year. Yeah. And when people explain how to do it, that's helpful. That's kind of why I like that we have the Discord. It's not like I'm trying to like Big Brother watch everyone, but like I think people know in the Discord, if you start sharing like a project that someone did from previous semesters, then that's a big problem. Yeah, some people do cheat. So I realize, and when we look into these things, we're not trying to get everyone in troubles. Yeah, exactly. Yeah, exactly. Like if people are sending projects or stuff like that, like then you're like, oof. And a lot of times it happens in like in these private messages in these groups. Like people are not usually bold enough to post it, like blatantly for people to see. A lot of times someone's probably covering their tracks, probably deleting stuff right now. Not saying you or anybody. Let me get the Proctorio thing reopened. But I was dealing with that in the background while I was. It's why I took a tiny bit longer to start the stream, dealing with the issues of stuff. Because it was kind of one of those more pressing things. Had to send emails out roundabout to people and instructors and say, hey, there's something new we got to deal with. Projects require too much work, so I don't want to share exactly. Yeah, and it's just a bummer. It's just, it makes my life harder because now, probably later tonight, I'm going to spend another hour or two dealing with this. And then one of the biggest problems I have is Brian complains about the things he hates about his job, is if I go to a student and I say, hey, there's a problem here, I usually know there's a bigger problem if the student really doesn't tell me much of anything. If the student is like very, 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 very not giving much information. If I go to someone and they give me very little information about what happened, they're like, oh yeah, someone shared it in the group me, that's it, that's all I'm telling you. When you get the least amount of information, that's where you're like, there's something going on right here. And then especially if they give you contradictory details. So when, if you ever have someone go to you, I haven't noticed anything bad in the group meets, but I don't want to look at them too much yet. Don't worry, we're not trying to get everyone in trouble. It's not even a 201 thing. So if you're in 201, don't start freaking out. Just don't do bad things in group meets. That's a good way to, I think the Proctorio thing's still open. We'll put it on whatchamacallit, Halloween. But yeah, just if you see something, it's best to report it and say, hey, I was in this group me and people are sending around projects or whatever, they're sending around assignments. If you're seeing this from there is a tool on group me, I think. Yep, it's a tool on group me. So if you ever see someone, please report it. It makes our life easier. Really, Sophie, really, the group me is actually dead? Well, that's interesting. Well, I think the Stats 1 Discord is doing pretty well. It's not that sometimes. There we go. Maybe there's a different one. If you're using these things, so let me just say this. I'm gonna throw 100 points out here. If you're using these things for good, like learning, helping each other, explaining problems, that's the way to do it. If you're doing these things to help out each other and to work with each other, that's the way to do it. If you see something you think ever violates codes of conduct, like someone says, like, here's a project, here's my friend's project from previous semester, those are things where you say you shouldn't be sharing like people's past works. Maybe you don't even say that. You might just go to like someone like me and say, hey, I'm in this group me and people are sharing old projects or something like that. It's best to do that. I've had students do that, and it actually makes it easier because usually we can like stop it immediately, especially if it's before people turn stuff in. Like then it literally, it's like an infection. Does that make sense? Like if the projects get like shared or something like that, if someone shares like an old project, it's like, hey, use this, I've got this template you should use, and like it's going to help you with the project, and you're like, I don't know if we should be using a template from someone, like someone made this thing to do, like, and it's their work that they're just telling us to fill in things, then that stops people from using it, and that stops us from having to deal with more plagiarism incidents and stuff like that. But if it's past the due dates and stuff, more people might be like, I'm busy, I don't have enough time, I'm just going to do the easier thing. As a group, me trying to talk to someone has Stat 201 or math. Oh, thank you so much. And I just want to be positive. It's the least fun part of my job, dealing with this kind of stuff. So with that, we've got everything reopened right here. I've got the notes saved. What are we going to work on? What are we going to learn? And then Tiffany, I saw that about the project grade. We'll take a look at that. I'll take a look at that. I saw that when I was doing all this stuff. How many exam questions is on the BAS? Oh, is that Josh and Flynn right there? Just got here. The BS exam has, I think, like 30 to 40 questions. Some interpretations in your exam too. What do you want to talk about, Josh? Can you explain Canvas content quiz? Yeah, let's do it. Let's do a Canvas content quiz. That's due tonight, right? Thank you, everybody, for dealing with grouchy Brian for a second. Thank you for dealing with me. I'll just always give you my honest opinion on stuff. It's confusing. I see the topics in the chapter slides. Yep. Let's take a look at some Canvas content. You bet. Chapter Canvas content. Let's do that. Here we go. The group me could be more interaction, maybe deadline reminders. Yeah, that's good stuff right there. Yeah, that's, use these things to learn. Don't use them to, wait. Okay, wait. Did I open up the wrong thing for the wrong class? No, that's a different thing. Let's go look at some Canvas content right here. Use these things to help yourself out. Pearson and Spearman, you bet. We'll do the Canvas content, then we'll do Pearson and Spearman. Thank you, Josh, right there. Great stuff, everybody. I'll get Brian Pack positive right here. But yes, if anything I said, if you've heard anything, if people are talking through the grapevine saying Brian's investigating something right now, please just email me if you know what this is all about. Because someone might have already been like, hey, Brian's on the hot trail on something right now. Just make my life easier. Tell me what happened. And just make my life easier. It makes my life so much easier. So once again, just want to put this out here as a PSA. If you heard Brian talking about some problems with a group me and some sharing of things that shouldn't be shared, like sharing of keys, if you know anything about this, please just email me. We just want to know what happened. We want to start figuring this out. You help me out. Big solid favor. Let's go talk about this Canvas content. Get off the topic of the not so fun stuff. Let's go talk about this Canvas content. Where's Canvas content at? Canvas content number... Where is it? I really can't see it. I'm blind. Canvas content number 7. Let's go check it out. Canvas content. Here we go. Let's check it out. It should... I'll have to check that out. Let's go everything. Oh, you bet. We'll go over everything. So this is the practice quiz. The Proctorio, Tiffany? I might have to change that after this. The Proctorio is not letting you do another attempt of it. I'm going to have to reset that. So let's go ahead and look at the questions right here. Oh, wait. I got to do another preview of it. So I think the question was, can you explain according to the central limit theorem? According to the central limit theorem. Do we have that one on here? No, we don't. Let's try to do another version of it. Will it give us that version? Can't resubmit it. According to the central limit theorem. We're going to try to get that one right here. If we can eventually get it. According... Oh my gosh. We're never going to get it. We're trying to get that according to the central limit theorem. Which I think I know which one you're asking about. According... Wow. We're going to try one more time. Oh, according to the central limit theorem. According to the central limit theorem, which of the following will happen to the distribution of the sample mean as the sample size increases? So when we do the central limit theorem, what does the central limit theorem state? I can cover this one without showing it. Yeah, no, I can do this one right here. You ready? Here is the distribution that we have up here. Now, the central limit theorem states that the distribution down low will be two things. And maybe it'll help if I draw the top distribution like this. The distribution up top, and it's probably going to be more like this. So this is what we call the parent population up top. Kind of the original distribution of single observations. And then the distribution down here on the bottom is the distribution of means. Now we're getting serious. Now we're learning. So this is the distribution of means down below. So with that being the distribution of means, what two things do you notice happen to it? What two things do you notice happen to it? What two things do you notice happen to it? So I want you to look at it, and it's just like this right here. We have a skewed distribution up top, and then we take 25 observations, and we see what happens to the distribution of means. So what happens to the distribution of means down here, Ashley? If you take a look, and this is just like the drawings we just did, so this is right here, it gets more normal. You bet right there, Kayla's got one of them. It gets more normal. And then what else do you notice too? Does the mean change? Does the mean change for the distribution of means? Does the mean change for the distribution of means? Does the mean change for the distribution of means? Does the mean change for the distribution of means? Does the mean change for the distribution of means? The mean does not change. What does change about the distribution of the mean? So the distribution of the mean will have a wider standard deviation. So the distribution of the mean has a wider standard deviation. Mean does not change, but the standard deviation gets smaller, which means the distribution gets tighter by a factor of square root of n. You can mathematically solve this out right here. Remember, it's 25, so square root of 25 is 5, and 6.22 divided by 5 is the new standard deviation. If I increase the simulation right here, this will go to 1.24 because that's the truth. Ooh, we got to do a lot of increase. It's eventually, I hope. Oh, it's so close. It's going to do it. It's never going to do it, right? Oh, man. Oh, there. Oh, look. It finally did it. It's so close mathematically. Like, there it goes. It finally did it. 1.24. Go back. It's so close mathematically to 1.25, but I think this would eventually converge. So this webpage right here is the sampling distribution applet. Here it is right there in the chat. I think I just did it right. Not next spring, but I will be, I think, the following, right? The following fall. I think I go on-off teaching 14.4, but we'll still have Stat Nation. We'll still be here helping out. I'll still be answering questions. I can do stuff on office hours if you want, Josh. So take it at any time. We'll be here helping out. And Dr. Lou usually teaches it. He's amazing. Great stuff right there. So I think, Ashley, does this answer your question about what changes and what does not change? So I think you can see it now. The mean does not change. The standard deviation gets smaller by a factor of the square root of the sample size, and the distribution gets more normal. So those are some great answers right there. And so the distribution of the original parent population might not be normal, but would have a mean and standard deviation. If we have a large enough sample size, large enough n, then this will be normally distributed with the same mean. The mean will be the same. That doesn't change. But the standard deviation is going to be right here. I want to say thank you. Don't worry, I'm not mad at everybody. I never want to come in here with negativity. Thank you for the start of this stream where I was a little negative, Brian, but I really appreciate it. Sometimes you just have to, it's just like the worst thing. I hate that stuff. Let's look over the rest of the campus content. The 3 conditions, I thought I removed this. Oh wait, no, this is a correct thing. The 3 conditions for the sampling distribution must be met in order to calculate p hat. How do we calculate p hat? Who can put the equation for p hat? If I tell you I speak to 200 people and 50 own a dog, you should be able to calculate p hat. Oh, it's a different class. So if you're freaking out in 201, it's not 201, it's a different class. So it's hard. Thank you so much, Tiffany. Yeah, it's not 201 related. It's different. I've contacted all the instructors for the other class. Thank you so much, Madison. Thank you so much. So if you're 201, just take a big, woo, everything's good. Everything's good. We're going to try to figure out the scope of it and everything. Just didn't want to have to deal with that kind of stuff. But okay, good question. Caroline asks, so Brian talks to 200 people and 50 own a dog. Thank you, Ashley. Brian talks to 200 people and 50 own a dog. So what is p hat? And what is p hat? So like mathematically, what is p hat? And then what is p hat? Woo! So Brian talks to 200 people and 50 own a dog. Solve p hat for this. And the answer is you do not need to meet the 3 conditions. That's what you need to meet normality. So p hat is the sample proportion. So out of 200 people, 50 own a dog, 50 is x. So 50 is x. Great job, Caroline, right there. Good practice. 50 is x. So 50 is x. N is 200. So what is p hat? P hat is the equation x over n. So think the sample proportion of people who own a dog. So what would that be right there? So 50 people out of 200 own a dog. So p hat is the sample proportion. So p hat is what in this problem that I just made up right here. No, Caroline, this is practice. Caroline, another 100 points. Don't worry. This is just practice. We're just here to practice and review multiple times. Ashley, you got it right there. Caroline, you got it. Look at that. Bad day turned to good day just immediately like that. You got it. We don't need to meet the conditions. We need to meet the conditions for things to be normally distributed. You can calculate p hat from x over n at any time. It's just how many out of the truth. This question someone asked about recently. I think it's a very good one. We have here the success failure condition, which says we need at least 10 successes and at least 10 failures. What 2 values, if we're checking to see if NP is greater than or equal to 10 and NQ is greater than or equal to 10, what notation should you try to find in this problem right here? What notation should you try to find in this problem? So this is tricky if you're looking at this right here and you're like, okay, wait a minute. They're asking about the success failure condition. This is probably one of the harder questions. I think a lot of people get this one wrong. So we're asking about the success failure condition. So you might want to identify what in notation. There's extra notation here that you don't need, and I think it's usually where people get confused. So what notation might you identify? Identifying notation is key to solving this. What do we need to find right here? We want to find for the success failure condition, we want NP to be greater than or equal to 10 and NQ to be greater than or equal to 10. Not quite. So what is 7,000? What is 7,000? Is it not opening? Sam, email me about that. If not, I think it is opening. Number 7 right here. What is 7,000 in notation? What is 7,000 in notation? We got this one here. We got this one. 7,000 in notation is what? N. Sample size. And then what is, now this is a trick. What is 500 in notation? We just covered this a moment ago. That's 500 out of the 7,000. So correct, Caroline, right there. Good practice. Oh, I'm on Top Chat. I wish it didn't go to Top Chat by default. What is 500? Great job. Yeah, people are getting it even quicker. X. Now be careful. If the defect rate is this, it's saying this is the truth. So what is that in notation? The defect rate, it's saying, let's say the defect rate is 3%. So what is that? It's saying, let's say the defect rate is 3%. Like if the defect rate is this. So assuming this is the truth. So what would that be in notation? What would that be in notation? So it's saying if the defect rate is this, then that would be what in notation? Close. It'll be P, which is true that we could say mu P hat equals P. That would be what we would expect to see in a sample. That is true. So it is P though, because it's saying this is the defect rate. So it is P, which could be used for mu P hat. So it could be the mean for what we expect if we take a sample, but it's saying it's the truth. So it's weird. Like we repurpose it then to say, what could we see in a sample? So now we just need to solve mathematically here 7,000 times 3%. And that one will be 21, right? No, 210. Wow. And the other one would be 7,000 times 97%, which is going to be the other side of that, equals to 6,790 if I'm doing my math correct. It should equal up to n. And you can double check your work right here. Always double check by throwing it into a calculator. Doesn't hurt to do NQ right here is 7,000. This is the bigger one though, so if the smaller one passes, this one's also good. So do we pass the condition? Do we have at least 10 successes, at least 10 failures? We do. We're going to do some Spearman and Pearson here in a second. So we have at least 10 successes. So it passes the success failure. Great job, Ashley, right there. Excellent work. 50 points following along. Love it. So it does pass the success failure condition. We have at least 10 successes, at least 10 failures. All other things being equal, the larger the sample size, the smaller the standard deviation. A good review of equations right here. We were doing those earlier. So if we have a larger sample size, what happens to the standard deviation? Everything else being equal, if the sample size is larger, which is n right here, what would happen to the standard deviation of this distribution? Or the other one? I'll draw the other one right here, or just put the notation. The distribution of the sample mean will have a mean equal to the mean, and the standard deviation will be equal to sigma over square root of n. So it will get smaller because we're dividing by square root of n basically in both instances. And so if the sample size gets bigger, everything else being equal, the larger the sample size, the smaller the standard deviation of the sampling distribution. Bingo. The sampling distribution of the mean will have the same blank as the original distribution. We actually just did that. So the sampling distribution of the sample mean will have the same what? What does not change about the distribution of the sample mean? The distribution of the sample mean will have the same what? So this is the distribution of the sample mean, or the mean for the sample mean is equal to the mean. It'll have the same mean. So the sampling distribution of the sample mean will always have the same mean as the original distribution. It will get more normal, so it doesn't always have the same shape, and it will get tighter. So it gets tighter, and it could get more normal. Like if it was skewed, percent condition says we need to sample what? Less than or more than? You got this. This is good practice. Hopefully people are acing these. But the 10% condition says we need to sample what of the population? So we'd ask ourselves, and we'll do one more review of this, and we'll do some Pearson and Spearman. We need to sample what of the population? How much of the population? Less than 10%, which is weird. No more than less than 10%. So let me ask you this. Do we pass the 10% condition here? So we are taking, oh, that was not X. That is sample size. That's population size. Ooh, I made an error. This is the population. This is the total amount. I thought I read it too quickly. Oh, and then I just calculated. Okay, we got very lucky. Ooh, I actually did this problem wrong, but got lucky. I got very lucky right here. Wow. Brian needs to... Wow, gee, I've gotten a few things wrong. That's sample size. That's population size. And hopefully no one caught that. I remember doing this now, and I've done this one correctly. So we still pass. We lucked out. We still pass. So less than 10% exactly. Temperature when you know true. Can you do a question? Assess failure. The conditions for sampling distribution of a sample mean when you know the true. Can you post the full question, Caroline? Post the full question. No. Are you talking about what are the conditions for the sampling distribution of the sample mean? The third condition. My gosh. The third condition would not be success failure. That's for categorical questions. The third condition will be large enough n. That might be the one you're working on. It might be large enough n. The condition for a sampling distribution sample mean when you know the true mean are condition 1. What's condition 1? What is condition 1 always? Condition 1 is always what? Condition 1 is always what? Condition 1, we always have to whatly. Kayla is right there. Randomly select. Condition 2 is what? Condition 1 is we randomly select. Condition 2 is we take what, which we were just talking about that a second ago. Condition 2 is we take what of the population, less than 10% of the population. Now what do we do? What do we do? If N8's here, they'll put it in the chat for us. What do we do now? What do we do now? I might have it on one of these sheets. What do we do now before we get to the next condition? Got to put it right here. What do we do before we get to the next condition? We don't want to use that one because that's one. Let's go to the notes sheet from last night. All right, Paul's all crazy like, oh, there it is. Look at that. So now we pause. And if it's categorical, we will go with success failure. But if it's quantitative, what will we go with? So now we ask ourselves, is it categorical or is it quantitative before doing the third condition? So since this one asks, are you in state, out of state, it'll be success failure. But if we had a question that was, and see if we have the notes on it down here. Let's go for large enough n. Oh, we don't have it on here. The third condition, we'll put it right here, would be large enough n. Large enough n right here if it is categorical, and it would say our sample size needs to be large enough that the distribution is nearly normal. There we go. I don't like when it goes around the thing. Okay. And so if normal, n needs to be at least 1. If skewed, but it's the for a sampling distribution of the sample mean. How do we know if that's cat or quant right there? So that says the sampling distribution of the sample mean. How do you know if that's cat or quant? Oh, yeah. So it says the sampling distribution of the sample mean. So how would we know what that is? It says the sampling distribution of the sample mean. So how would we know what that is? So this will be success failure right here for third condition. And this is quant. It's quantitative. Great job right there, Ashley and everyone. It's quantitative because means are like, like what is the average GPA? That's a mean GPA. I think people often get confused because in the notation we use like mu p hat equals p, so they see this mu right here, but the thing is this is categorical because of the p hat, where the other one is going to be down here mu, I hate that crayon, mu y bar equals mu, and this one right here is quantitative because the sampling distribution of the sample mean. Does that make more sense right here? Mu p hat stands for the mean for the distribution of the sample proportion, which is a categorical question, where mu y bar stands for the mean for the distribution of the sample mean, which is quantitative. And you also get standard deviations and stuff like that too. The equations are a little bit different. So this one down here, we've got the color coding to help out. I'll disappear for a moment so you can see it clearly on the screen. But just kind of reviewing this right here. If you're talking about mu p hat, p hats are categorical because you're saying sample proportions and like the proportion of people who are in state, out of state. And you'll be dealing with a yes, no type question. Where down here, if you have a large enough n, you're dealing with sample means. So you're dealing with things like GPAs. So this is the mean for the distribution of the sample mean is equal to the mean. The mean for the distribution of the sample proportion is equal to the true proportion. I think this mu right here often confuses people, but that's just telling you what to expect. So if it helps, say, I expect a sample proportion to be equal to the true proportion. I expect a sample mean to be equal to the true mean. So that should help out right there. Hopefully it makes sense. So whenever you see the sampling distribution of the sample mean, and here's a really good thing to do. Do this. So please take a look at the formula sheet. Might do another review like tomorrow or something like that. But take a look at the formula sheet because, and we're going to do some Spearman Pearson here in a second. The formula sheet shows you which conditions are what, or which, not conditions, but shows you the equations. So here's the formula sheet, which you can print off or write down before the test. Make sure to show it front back. And so if you look right here, sampling distributions right here, proportions are what kind of questions, C or Q? Proportions are what kind of questions, C or Q? So you can see the mean for the distribution of the sample proportion is equal to the true proportion. The standard deviation of the sample proportion is equal to p times q over n square root. And then this is how to find a z-score, which is your observed. And you got to ask you right here, this is all categorical. Like, do you own a dog? Are you in state, out of state? Are people freshmen? And then this one right here is all quantitative, like what's your GPA? How tall are you? How much do you weigh? All questions that end in a real number, because then we would take a sample mean, and this is what we expect if we were to take a sample of students. Like if I know the GPA of students is a 3.6, what sample mean would I expect to see given students have an actual GPA of 3.6 on average? That's got it right here. Let's do a new topic. You got it. It's open floor after this question right here. So if you have a question, especially for the test or for the assignments, if you're working on chapter 14, let me know. We're going to be covering Spearman versus Pearson right here. So we should get 100 on that quiz, right? Did we get 100? Should get 10 out of 10. Is it a good day today? You bet it is. 10 out of 10 right there. Got it. Okay, so let's check out some Pearson versus Spearman. A little bit of Stats 1 crossover here. So if you want to take 320 or something like that, a lot of good information. So when would we use correlation? When do we use correlation? Kind of a big thing right here. Who knows when we use correlation? Yes, I haven't posted the sheet yet because I don't have access to the Stats 1 webpage on this computer because I have to be on the virtual network or the VPN, which is on my laptop. But I'll have that posted here after office hours, Tiffany. Yep. Because I just can't access. I have to send it myself and do all stuff. When do we use correlation? Now, if you're 201 or 320, you might know this. Thank you, Colin, right there. I saw your emails. I haven't replied to them yet, but I saw them just a little while ago. Colin, 100 points. Thank you, Colin from Disney, sending some pixie dust. We're going to plan something out with the Business Analytics Society. Colin, thank you so much. Colin, you're throwing some positivity. I had to deal with some not fun stuff, but you're throwing that positivity out here. Love it. When do we use correlation? You should know something, straight enough. No outliers. Correlation is used when what? We're going to talk here about Pearson versus Spearman. Pearson versus Spearman correlation. When do we use correlation? Kind of what variables? Like when we have two of these variables, we can talk about the correlation between them. Like you wouldn't want to use like gender and favorite restaurant in Knoxville. Those aren't correlated. That's not going to be correlated. You can't use somebody's class level and what courses they're taking. That's not correlated. You might say, well, don't seniors take more like higher level courses? I might be able to do it that way, maybe. Two quantitative variables. Sam knows what's up. Great job, Sam, right there. Quantitative. Two quantitative variables. But now we're down to these two types of correlations right here. So let's draw a few graphics. What do we want? We're going to draw some graphics right here and talk about these things. So we've got this, and we've got this. Not graphics yet. We got this one right here. And then we got this one right here. And then let's go this one right here. You know what? Let's draw 6 graphics because we can do a lot more. Let's draw this. We'll draw 6 total graphics. We'll talk about what correlations, kind of drawing every possible relationship. Can you talk to correlation? Yeah, here, we'll do that next year, Tiffany. You got it. Thank you so much, Tiffany. We'll, I don't know why it wouldn't let you retake it. I'll put more attempts if it's saying you don't have enough attempts. This is decent for 201 right here on reviewing some concepts for regression. And so let's talk about all these graphics right here. Okay. What graphic do you like the most right here? If you're 201, whatever class you're in, what graphic do you like the most? Who has a graphic they really like on this screen right now? Hey, hello, Jacob. Good to see you here. What graphic do you like the most if you're 201 looking at these scatter plots right here? So we can use correlation for two quantitative variables. And what graphic do you like the most? Ashley, big fan, number 1 right there for 100 points. Big fan. So Pearson correlation used when there is a linear relationship, no outliers, kind of like QQ straight enough, no outliers, no heteroscedasticity. Did I spell it right? Might have got it. This is plot does not thicken. So let's kind of look through these right here and see if we can figure out the issues. Now, the first one right here, great job, everybody. I'm throwing more points. I'm all happy to deal with all those points. So if you look at this first one right here, it's two quantitative variables. One, because it's a scatter plot, it has to be two quantitative variables. So this follows two quantitative variables. What is the problem with number 2 with using Pearson on number 2? What is the problem with using Pearson correlation on number 2? So we probably don't want to use Pearson on number 2. Why? So Pearson could be used on number 1. Why are we not going to use Pearson on number 2? It's not straight enough. Does not follow a straight relationship right here. So we're not going to use Pearson on number 2. We'll highlight Pearson like this. What's the problem with number 3 in using Pearson? So why would you not use Pearson with number 3? Pearson number 3. Oh, the answer, don't worry, it's a repeat answer. Pearson on number 3, same answer, not straight enough. What's the problem with Pearson with number 4? Here, we'll highlight some stuff right here. We want there to be a linear relationship. Linear relationships are good. Linear relationship is a good thing to see. So put that in green. We want there to be no outliers. Outliers are bad. Bad. Outliers are bad, and we don't want there to be plot thickening. So for number 3 right here, we see an issue with, and maybe we'll highlight that in red right there. We see an issue with the outlier down here. So that's a problem for Pearson. This lack of linear relationship right here is going to be a problem for Pearson. There's an outlier. Great, Nate. It's good to see you. Some points for Nate right there. And then also the problem with number 5 is going to be what right here, which is a regression condition. So good review for 201. The problem with number 5 for Pearson is going to be what? The problem with number 5 is going to be a what issue? Number 5 has heteroscedasticity. Heteroscedasticity means differing spread. Think of homoscedasticity, same spread. So this has homoscedasticity. It looks like it's the same spread across, where this one has a differing spread, differing hetero spread. So that we don't want heteroscedasticity. We want the same kind of even spread. Now, the last one's a bit interesting. If you were to solve out Pearson right here, what would the last one basically solve to? It's not like Pearson's a bad idea, but what would the Pearson solve out to for the last one? It's kind of like, whatever. What do you think Pearson's going to basically solve to for the last one? It's not like Pearson is bad for that, but it just doesn't do much. What do you think Pearson would solve out for the last one? When we look at the linear relationship right here, if we were to put a line through this, this might help. What do you think the Pearson's going to solve to for that one? Which, interestingly enough, if you remember up here, the Pearson over here is also going to solve to that. 0. Great job. Kayla, you got it. And the Pearson for that one also solves to a 0. So this solves to 0 because it's not well described by a line. This one's actually more true 0 because there's really nothing going on. But interestingly enough, those two right there and there solve to 0. So with this, we now have to ask the question, what is Spearman? Now, the way I like to think about Spearman, do any of these look like an S? Would you notice any of these right here that look like an S? Do any of these right here look like an S? I'll write about Spearman while you think about that question. Used for monotonic relationships. Really? Used for monotonic relationships. Deals with outliers. Really? You're just having fun with me there, aren't you? Why Deals with outliers and hetero. Oh, look, it's going to fit. Hetero skidasticity. It's almost like, thank you very much, Sam. It's almost like this is going to deal with a lot of our issues. It's almost like this is going to deal with a lot of our issues. Does that make sense to everybody here? It's almost like, oh, look at that, much better. It's almost like this is going to deal with a lot of our issues with the plots. Does that make sense? So 2 looks like an S. So does anyone know? You might need to know your favorite band for this, but does anyone know what monotonic means? Does anyone know what the word monotonic means? We'll put some Spearman stuff in orange. Think of your favorite band right here. You got to know your real favorite band. Does anyone know what monotonic means? A plot that goes in what? Who knows what monotonic means? Monotonic means, break down mono, and then think your favorite band. A monotonic plot goes in what? Your favorite band. Close, Sam. Your favorite band, though, not one tone. You don't know of the band One Tone. 100 points if you know your favorite band. Not one tone. Monotonic means it goes in one. Favorite band right here. Remember what monotonic is. Your favorite band of all time. What is it? What's his name of the guy in the band? Can't think of it anymore. One Direction. Goes in one direction. Best band ever. Just huge fan of One Direction. Oh no, Kayla says, oh no. One Direction right there. Is that Zayd? I don't know the guy's name. Can't remember it. One Direction. Does that make sense that plot 2 goes in one direction? Harry Styles. There we go. And Zayn. Gosh, it's sad that I know this kind of stuff. Is this a monotonic relationship? Yes or no? Is plot 3 a monotonic relationship? Is plot 3 well described? Is plot 3 monotonic? Look at plot 3. Is plot 3 monotonic? So this one deals with the outliers. Is plot 3 monotonic? Yes or no? It's a good review right here. Is plot 3 monotonic? Is plot 3 monotonic? Does plot 3 go in one direction? No, I don't think. Exactly. One direction means that there goes, the line is monotonic. This is monotonic. It goes constantly up. It means it goes in one direction. This goes in one direction. This does not go in one direction. See how it goes up and then it goes down. So this one would not be well described by either. We cannot use Pearson or Spearman for this. That's going to be too dark or too matching on it. That one's not going to be Pearson or Spearman. Does that make sense? That one's not Pearson or Spearman. But now that we're down here using Spearman, Spearman can deal with outliers. So number 4, can we use Spearman for number 4? Spearman can deal with outliers. I haven't gone into the mathematics on how it deals with it, but Spearman will downweight outliers. It's called rank correlation, so it gives them ranks. I could go into the mathematics. You're exactly right, Carolyn, right there. 201 is just practicing some 320 right here. If you're wondering, this is 320. And then what does also Spearman deal with? It also deals with heteroscedasticity. So guess what? Spearman can be used here. This last one right here is kind of where neither are really well used. It's just not going to be well described by either because there's no relationship to y and x. It's just kind of like you got nothing. This one's not good. This one's not well described by Pearson or Spearman. So this one violates both. But you can see right here where we see when do we use Pearson. This is stat tool 1 right here. You want a linear relationship with no outliers, limited heteroscedasticity. And so you can see right here, QQ straight enough, no outliers, plot doesn't thicken. You go right here to using Spearman, and it still has to be monotonic, though. Lines are monotonic. They go in one direction. A line, no matter how you draw it, will go in one direction. But the thing about Spearman, though, is that the relationship no longer has to be this. When you go to Spearman, the relationship no longer has to be what? Spearman deals with what kind of relationships? Not this relationship. Relationships that are not this. Spearman can deal with a relationship that is not this. It still must be monotonic. Spearman deals with relationships that are what? Spearman helps us describe relationships that are what? Non-linear, exactly. And then if we have something that is non-monotonic, neither of these are going to work. If there's outliers, we're going to see right here that this will work better. And what's so great is, and I love showing people how to code, because we can go here and run an association between height and weight. I think I have these currently stored. And, oh, ooh, that's interesting. This is like, what data set am I using right there? I don't even know what data set that is. Let's go to an actual data set. That's a weird data set. So here we go. Would you rather use Spearman or Pearson on this? So if you're in 201, you might have just learned the difference between Pearson and Spearman, and I want you to explain to me why you would use Pearson or Spearman, and just take a look. I'll do some drawings right here, and you should start to see why we should use a certain one right here, and then the mathematics is going to show it. But if you look right here, I see this, I see that, and I also see something else. Which one of those would you use from our review? Which one of those are you going to use? I don't think there's much of an issue. I'm going to draw that in a blue pen. I don't see too much of an issue with this. Maybe a little bit, but that's my lesser concern. We've got outliers, and so we've got outliers. Not Sam just crushing it right there. Sam, are you 201 or 320? I can't remember. Sam, 100 points, everyone. That's the exact answer, and I'm trying to illustrate there's a bit of a nonlinear relationship, and also we have here outliers. Sam, you're earning another 100 points. Yeah, you just learned the difference between Spearman and Pearson. And take a look at this right here. And it is monotonic. Kayla, great job right there. 50 more points on top of that. So it's monotonic. It goes consistently up. So it can be well described by Spearman. Guess what the values are for Spearman? Just like Pearson, if you look at Spearman values, you notice how Spearman is higher, like the Spearman's picking up on it more. Spearman has values between what and what? Spearman has values between what and what? Spearman has values between what and what? Yeah, dude, Sam, you're crushing it, man. I'm so proud of you, Sam. I'm honored by everybody. Caleb hung out for the 320. I was honored by that, Kayla, last night. You know I was. I'm just honored when people are here just checking out, like trying to learn the new things. What do you think are the values of Spearman correlation? What do you think are the values of Spearman correlation? Spearman is going to go as low as this or as high as this. And I'll show you the lowest possible value here in a second. Spearman could go as low as this or as high as this. It's just like Pearson. Just think of it as Pearson. And I could explain to you how it works. I might do that real quick here. I'll explain how it works after this. I can do a small data set really easily. So the lowest Spearman can go, close, not zero. It's just like Pearson. If you do 320, this, and see, it's a lot like we do in 201. That's why I tell people, like, if you learn in 201, it just carries over. Just like Pearson, Spearman can go as low as -1. And so this has a perfect linear and perfect monotonic relationship. Great job, people following along. But I want to show you how it really downweights outliers. So take a look at this vector of x. These are the values 1, 2, 100. And so now let's go here to the values of y, and let's go here to 1, 2, 3. If I go to plot x and y, we won't make y so far out. Let's go here to 20. Does that make sense what you're seeing right here? Your political science. Well, no, I could put you in contact with someone who's doing a PhD in political science. He actually did a lot of business analytics courses. Alec, I won't say his last name here, but he's one of my former students who got a PhD. He's getting a PhD. He might have it by now. He finished school about a year and a half ago at UT. But he's going on to a PhD in political science, and he did a lot of like research and everything, and uses a lot of statistics and data, and knows advanced techniques, and it's helped him. So data and data techniques are very impactful. What do you notice about this relationship right here between x and y? And we could add in another value over here, like 40, 4. What do you notice about the relationship of x and y right here? What do you notice about the relationship of x and y? The relationship, I want to put this further out. The relationship of x and y is what right here? The relationship between x and y is very what right here? The relationship between x and y is very not this. The relationship between x and y is very not this right now. X and y have a very not this relationship. You might think weak. You might think well, you are correct. It's not a very good what this relationship. I'll give you a hint. It's not a very good what relationship. It's not good linear, exactly. It's not a very good linear relationship. But what if there was some way to draw like a this relationship right here? And how strong would this relationship be? Weak, moderate, or very strong? What do you think if we draw the relationship like this instead of a line? Like instead of drawing a line, we draw the relationship like some sort of curved relationship. I would say that that'd be much stronger, right? That red line, right? That red parabolic relationship is much stronger. How about if we go to the x, and I'd like for you to tell me on the x-axis, and it might be hard to see, but I want you to label right here this point right here on the x-axis. What x value is that? Is that the first x, or is that the second, or the third, or the fourth, or the fifth x? So Is that the first X from the left to the right, or is that the second, or is that the third, or is that the fourth, or is that the fifth? Hint, it has value 1. So is that the first, the second, third, the fourth, or the fifth? It's the first. And because if you look at the values I created for this, just if you want to see again, the values created for this, that is value 1, 2, 3, 4, 5. It might be hard to see because the number line's so scrunched. It is the first, Kelly. You are correct. 50 points right there. That is the first. But now, no, not but now. This is the second. This is the third. This is the, does this make sense what I'm doing? I'm just looking across the x-axis and doing this right here. But now let's go and let's ask about the y-axis. So now on the y-axis, what is this value on the y-axis? Going up and down from the y-axis, from the bottom to the top, like from the bottom to the top, what is that on the y-axis? On the y-axis, that is the what? On the y-axis, that would be what? And what we're doing right here is we're giving them ranks. We're saying on the y, you are the blanked y. On the x, you are the blanked x. We're just putting them in a rank order, hence Spearman rank correlation. It's not, wait, so the one we've circled right here is the what. From the bottom to the top, the one we've circled right there is the what y value. From the very bottom, if you go to the very bottom and say, this is where we're starting, that is the what y value. And we're only looking at its y. No longer are we looking at the x, which is in green right here. It's the first. So that's the first. Does that make sense? And then this one right here would be the what, just to follow along. That would be the what y value. That's going to be the what y value. Yeah. And so that's going to be, for that one, that's going to be the what. For in terms of y, just going up and down on the y from the bottom to the top, that's going to be what? Second. Third. Wait a minute. Do you see something about these ranks right here? Like if I were to take and plot the ranks, how would it look if I plotted the ranks right here? Like if I take those values I just wrote, and I go down here to the bottom, I wanted black, and I go down here to the bottom, and I use those x ranks, like the ranks of x, what would the relationship look like if I plot this right here with the ranks? And that's what Spearman rank correlation is. Do you see it? The Spearman rank correlation right here would be what? Like if we say the RS, which is Spearman rank, the Spearman rank correlation here would be what? The Spearman rank correlation would be, it is linear. It actually turns it into a linear relationship. This was a nonlinear, and the ranks are linearly related. You see, like we got this outlier, we got this nonlinear relationship. The value of the Spearman rank correlation here would be what? Which is what we're calculating by finding the ranks and then correlating the ranks. The value of it would be, so think of it just as normal correlation now, even though we're using the ranks. It'd be 1. Great job, Sam, right there. It'd be 1. And all of this can be done instantaneously for you right here just by running the associate function. And we go to associate y comma x, or y tilde x, excuse me. That's the formula format. And there it is right here. And there was actually a pretty decent linear relationship, but the Spearman rank correlation is 1. The Spearman rank correlation is 1, and that's what we see right there. If it were to be monotonic down, which we should be able to do by doing y save into negative y, that should do it. And there we go. And do you see now it's negatively rank correlated? Like as the rank of x increases, we see a decrease to the rank of y. There is a linear relationship, but the nonlinearity here is pretty present. But there is a negative rank correlation. X increasing in rank decreases y in rank. I flipped the y and x. So this is negative rank correlation right here. And it's very, very strong negative rank correlation because it perfectly follows a monotonic, like it constantly goes down. So it's a very good rank correlation. Is this concept, so if you're in 201, hopefully you got to hear some new stuff right here and learn about rank correlation. But yeah, that is how we do Spearman rank correlation, which is not on your test. And here's the key notes on when to know when to use each one. Spearman rank correlation must be this. Spearman rank correlation must be this. What is the key thing you see me starting out with? And the key new words you might have learned right here for this. It must be this to be Spearman rank correlation, which number 2 with that S right there is really one of our keys to knowing it. And you can see the color coding. Spearman rank correlation needs to be this. You might have an instance where neither of them are a good idea. This is a neither idea right there. Spearman rank correlation must be monotonic. Sam, great practice right there. New words to learn about. Let's head back here to the main screen. We're going to fix that thing Tiffany asked about. Let's fix that thing. And then we're going to do a new question. Great practice. A really good review of Spearman versus Pearson and when to use them. So if you're 320, check that out. Da-da-da. Gonna fix the 201. Let me get the Proctorio I thought it'd be reopened, but it might have had like a limit on the attempts. Where's the practice? If you have questions, put them in the chat. Where's the practice? Proctorio. October 31st, I would set to now. Test your system. There's test your system. Edit. Edit. Oh. Did it not save? Allow multiple attempts. Did it not save? Tiffany, is it open now? It says it allows multiple attempts. Tell me, Tiffany, if it's open. One of them might not have saved. It might have saved for one class and not another. You want to do some distance trees? It should be open. Tell me if it's open now. Because if it's not, I don't know what's happening on it. But I went and re-clicked the buttons to open it. And the exam date, does it say October 31st open till? You might send me a screenshot of what it's saying is wrong. We'll do some distance trees. Distance trees coming up next. Good stuff right here. Tell me if it says it's open, Tiffany, or if it's working. Send me a screenshot if it's not working. But it should be. Hey, Dan, good to see you here. Dan, haven't seen you in a while. 324.74, right, Dan? Your Canvas content. Let me see out that, Sam. Let me go look at this. Let's try to fix that now. Sam emailed me. Okay, Sam says, can you send me a screenshot of it, Sam? Can you reply to this one with a screenshot? Reply with a screenshot of what's going on. And so send me that screenshot. Let me write a quick reply to this. Working as a team. Let's see right here. Can Brian fix it? What is the thing that needs to be fixed? It says it needs a code for a few seconds, then it takes me off the screen. I think you might need to check your browsers and stuff. So there's going to be an error message after all. See, my Canvas content. So if it says you need the code, Tiffany, you need to recheck your Proctorio stuff. So Tiffany, it should never ask for a code. When Proctorio is working properly, it won't ask for a code. So maybe try resetting, but Proctorio won't ask for a code. If there is a tablet. Sometimes I think I want kids, Kayla, and then other times I'm like, no. That's a no. Sometimes I'm like, I'd want kids, but yeah, if it says you need a code, you need to check your browser, check the Proctorio. It shouldn't ask for a code. If it says it needs a code, that's not an issue with the settings I have up. That's an issue with checking the browser. Having a pretty good day dealing with a thing in the background. Other than that, pretty good day. Sam, send me, although if you can send me a screenshot of that, Sam, I'll take a look here. Yeah. Yeah, call OIT. So big thing, update all the browsers and stuff. So update all the browsers and stuff. Let's see right here. I'll see if Sam sent me a reply. Oh, Sam sent me a screenshot. Okay, right here it is. So what happens when you do take the quiz, Sam? So you have thank you, Sam, for sending this. What happens when you do take the quiz? Does it not open? When you do take the quiz, it does not do anything. Oh no, and you said you tried multiple browsers? All right, thank you for messaging me about this, Sam. Nothing at all. Okay, here's what we're gonna do, Sam. We're gonna do something special here, Sam. We're gonna fix this. I think you're the only one having this problem, Sam. Okay, so Sam, We're going to teamwork this out. You ready, Sam? Sam, we're going to take your quiz with you right here. Sam, you get the benefit. Thank you for contacting me about this. I don't know. Try Firefox and tell me if it works. And if it doesn't work, we're going to have a fix. So give me a quick update on that right here. And if it doesn't work, we're going to fix it right here. And we're going to work on it. So that way you can get an attempt at it. Because I don't know. No one else has contacted me and saying theirs isn't opening. The condition for the distribution of the sample mean, when you know the true mean R. So what is condition 1? Let's go review some conditions right here. What are condition 1? What is condition 1? I'm going to find that sheet we were working on right here. What is condition 1? Who knows some condition 1 right here as Brian finds the sheet that has everything written on it that we need. What is condition 1? People know that condition 1. Condition 1 is what? We're so close. We're so close. Oh, it's going to be this one, right? There it is. Condition 1 is random. Condition 1 is random. Condition 2 is always what? Condition 2 is always what? Condition 2 is always that we sample what of the population? So condition 1 is random. Condition 2 will be that we sample what of the population? Condition 2 is that we sample what of the population? So condition 1 is random. Did we randomly sample? Condition 2 is less than 10% of the population. And now what do we do when we get to condition 3? What do we do? No more than, less than 10% of the population. Now what do we do when we get to condition 3? Before doing condition 3, we always do this. And so, Ethan, this will kind of answer your question. So before we get to condition 3, we always pause. We always pause here. And then we ask ourselves, are we dealing with a categorical or quantitative question? So we ask ourselves, is it a categorical or quantitative question? Pause right there in the chat, 50 points. And so with this, when we are doing the sampling distribution of the sample proportion, that means it's categorical. And categorical data will have the success-failure condition. So we need at least 10 successes, at least 10 failures found by finding N, P, and Q and checking NP greater than 10 and NQ greater than 10. So we passed it in this example on the screen. Now the other condition right here, and great job, Kayla, right there. The other condition is the large enough N condition, which is checked by looking at the original shape of the distribution and asking, do we have a large enough sample size for that shape for it to be nearly normal? On that condition later in the semester. So with this right here, if it is normal, we only need an N of 1. If it is skewed, we need an N of 25. If it is very skewed, we need an N of at least 100. So if you notice, the more skewed it is, the larger N needs to be. So it kind of deals with that skew, and this deals with the central limit theorem on the shape of the distribution of the sample mean. So means are quantitative. Means are quantitative. So if you're dealing with the sampling distribution of the sample mean, which this says, we expect the sample mean to be equal to true mean. This is the distribution of the sample mean. This is the distribution of the sample proportion. We expect the sample proportion to be equal to the true proportion. And these are all categorical questions with the success failure. So hopefully the color coding here helps some to kind of see it. Ethan, we don't want to quite say the answer, but you kind of get the drift about the difference between when we use success failure and when we use the large enough N condition. To see the difference here between success failure being a question like, do you own a dog? Are you a freshman? Are you born in Tennessee? We're down here, it's like, how much do you weigh? How tall are you? These are all quantitative questions that give us actual real numeric answers right here. And Sam, how are we doing, Sam? Was it able to work in Firefox? If not, we're going to have I've got a solution right here. So thank you, everyone. We're getting things fixed up. It's just like good old office hours right here where we get things fixed up. All that good stuff right here. We'll see what people are saying. Great stuff. Successes or failures. And that's how we do the conditions. And for the remainder of the semester, these will not change. For the remainder of the semester, you're going to hear me yell out condition 1, condition 2, condition 3. Well, then we pause. So those conditions do not change for the remainder of the semester. So if you know condition 1, it's random. Condition 2 is 10%. Then you pause and you ask yourself, what am I dealing with? What chapter am I in? So awesome, Sam. I got a way to fix it. We're just going to take it together probably here. So if it doesn't work for you, we're going to take it together because that's not going to have somebody not be able to take it. It looks to be just a random issue. Random. If it doesn't work, we're just going to take it here on stream. We'll count it because it's one of those, like, we just deal with things that they happen. We just fix something and deal with it. My fiance made a 7-layer dip last night. Oh my gosh, that was good. We watched the end of Fear Factor. Couples Fear Factor. God love some Fear Factor. Joe Rogan, of course. Only Fear Factor is with Joe Rogan. Heard him talk about one time about the things they did. Yeah, it was so good. So good. Had like churro bean dip. Had lettuce. Had salsa. Guacamole. Sour cream. Cheese. Gotta have cheese. Like everything good. Everything good in life was on that. Had love and enjoyment and all that good stuff. Brave. Oh, yeah. No, they did a few stunts. I guess you watch enough Fear Factor, you get used to it. Like, tonight, you're eating this. I think they had, like, blended. It's working on Firefox. Sam, good job right there, Sam. 100 points. Thank you for... I don't know what's going on with Chrome right there, right? Chrome, what you doing, man? Chrome, why are you being weird? Yeah, I hadn't heard the problems about that, Sam. So thank you for checking that out, Sam. If it didn't work, we were just going to do it on stream, and that'd give you the points for whatever you get. So just because, I mean... I think it's ridiculous if a student wouldn't be able to do it. You got it, Sam. You got it, Sam. Let's do one more version of the Canvas content while Sam's working on that. If you have a question, please let me know. We're going to do a version of the Canvas content while Sam's working on this. Just to review and see if we can get this down. Let's practice. So here's another version of the Canvas content. All other things being equal, the larger the sample size, the smaller standard deviation. So all other things being equal, the larger the sample size, the smaller the standard deviation. Is that true right here? We have it over here. Is that true that all things, you bet right there, because either equation you use, if you use the equation up here for this one, it'd be SD P hat equals to P times Q over N square root. Since N is on the bottom, larger sample size, smaller standard deviation. And the bottom one down here is SD Y bar, the distribution of the sample mean, has the standard deviation of the original distribution divided by the square root of n. So you can see n is in the bottom of these equations. Larger sample size, smaller standard deviation. That's 100% true. If you get a question like this on the test, you're like, hey, 3 points. The 3 conditions must be met in order to calculate p hat. Tell me the equation for p hat again. This is where you want to have it down. This is not on the formula sheet. Who knows the equation for p hat just like instantaneously is like, Brian says, we know UT is 20% freshmen. We go out and talk to 40 students and 10 are freshmen. X over n. So what would it be for what I just said? We know UT is 25% freshmen. We go out and talk to, well, we know UT is 30% freshmen. We go out and talk to 40 students, 10 are freshmen. No, you got it right there. X over n. That is correct. So in what I just said really quickly, 10 is X. That is the number of successes. And 40 is equal to the sample size. So 25% of our sample. You do not have to meet conditions to calculate this. You just calculate p hat by saying how many freshmen were out of 40. You don't meet conditions. You just say, well, how many freshmen were there out of 40? So wait, whoa. We don't have to meet the conditions. Why do we meet the conditions? What's the whole point of checking these conditions? Why do we check these conditions? This is a great question right here. Why do we check conditions? We check conditions so we can draw the what for this. With checking the conditions, if we check the conditions, we can now find the mean and the standard deviation, and then we draw it on the what. The whole point of meeting these conditions is to draw this on the what. The whole point of these conditions right here, the whole point of meeting these conditions is to draw the normal curve. The whole point, whether you're doing the sampling distribution of the sample mean, the sampling distribution of the sample proportion, because these values will go inside of here. If we meet these conditions, you can then talk about the mean and the standard deviation on a normal curve. And that's what we're trying to do right here is we're trying to use these, and these will be used as the mean and the standard deviation for the curve, i.e. the mean for the sample mean and the standard deviation for the sample mean. So the point of meeting these right here, we'll do a little more highlighting. The point of meeting these is that we meet the conditions to draw the normal curve. You do not have to meet them to calculate p hat. That's just the sample proportion. A manufacturing company, we did this one earlier, we need to identify NP hat, or NP and NQ for the success failure condition. This is whether or not things are defective. So it's defective, yes, no. That makes it a categorical question. This right here is actually N because it's the sample size we're taking. This right here is P, so we calculate NP, which is 500 times 0.03, and that's the amount of successes we would expect. NQ is actually going to be the other side of that, which is 485. We could confirm that by finding Q, which is just 1 minus P. 1 minus P is Q. Write that down if you don't have it. And then we would times that by 500, and we do get this. Remember, NP plus NQ equals to N. So do we meet the condition? Both of these are greater than or equal to what? To meet the success failure condition, put in the chat, we need to have at least this many successes and failures. So to pass the success failure condition, we need at least this many successes, at least this many failures. And then we would find n, we'd find p, and we'd do np, find that, here's the one value, and we'd do nq, 10, exactly. So do we meet it? Yes. Both of those, we found 15 and 485. The 10% condition states do not sample more than, we need to sample no more than, less than 10%. And if the sampling distribution sample mean has all the conditions met, sampling distribution will always have the same what? So when we do this, here I'll draw it out on a new sheet. The sampling distribution of the sample mean is going to have the following equation. The mean for the distribution of the sample mean is equal to the mean. The standard deviation is equal to the original standard deviation over the square root of n. And then when we look at it here, visually speaking, you can see that the new distribution always becomes water. Exactly, it becomes tighter, and then what else? So it's going to have the same mean. There's mathematical. We just saw this equation written out, but this is the proof. Like it has the same mean, the standard deviation is smaller, and then it's also, it's tighter, correct? Smaller standard deviation, and it's also more this, which don't worry, we've said this like 10 times today, but if you get to a test question, well, you'll be like, oh, the distribution of the mean is going to be more normal too. As n increases right here, if we only do like an n of 2, it's still skewed, but as n gets larger, it gets more tighter and more normal, and we're now viewing it visually, exactly symmetric, unimodal. And so you could have something weird, like you could do a weird distribution like this right here, and that's multimodal, kind of multimodal right skew. And if you were to average together 25 observations from this, this blue dot is the average of 25 observations. So this new distribution down low, there it is. That's the new distribution. And the new standard deviation is the original standard deviation divided by the square root of 25, so you can actually mathematically calculate that number. Square root of 25 is 5, so let's take 8.67 divided by 5 and look at that. If we do it, it'll probably go down to 7.3 because that's what this says it should be. This is just doing the same formula as you see here on the screen where the mean is the same mean. Let's show that. The mean is the same mean. The mean down here, this is mu y bar because it's the mean for the distribution of the sample means is equal to the original mean. The original standard deviation of 8.67 is going to be divided by the square root of 25. I didn't put an equal sign right there. And it's going to be tighter by a factor of n. And then also it becomes more normal, which is another thing of the central limit theorem. The condition for a sample distribution of a sample mean where you know the true mean are. So what do we have to do? If we have right here, Ethan asked a good question right here. If we have right here the conditions, what would we decide? So the sampling distribution of the sample mean, is that quantitative or categorical? So is that quantitative or categorical, Ethan, or anyone can answer? Is the sampling distribution of the sample mean quantitative or categorical? So sampling distribution of sample mean, is that quantitative or categorical? So is that going to be a quantitative or categorical question right there? If we ask people questions about means. Sampling distribution of sample mean, is that quantitative or categorical? It's quant. So now condition 1 is always going to be random. Great job right there, Ethan. And Kayla too. So it's going to be quantitative. And then the next condition right here is going to be random. Next condition right here is 10%. And then when we decide that third condition, we have to ask ourselves, is it quantitative or is it categorical? So if we're doing the sampling distribution of the sample mean, the next condition will be the large enough n condition right there. And this is questions like, how tall are you? How much do you weigh? How much is your salary? How many miles do you run a week? Because these are all quantitative questions right there. Ethan's now a mod. Good to have you on the mod team, Ethan. Let's do one more version of the Canvas content. It'll have the same mean. Should get everything right. 10 out of 10. Love it. New question. We did this one earlier. Check it out. We've done it 2 times today, so this is met. Check that out. All other things being equal, the sample size, the larger sample size, the smaller standard deviation, the sample distribution. Very true. We did that one earlier. We do not have to calculate that. Oh, we've done these. Oh, here we go. New one, finally. The camera say no more than. According to the central limit theorem, which of the following... Hundo, God, I love those hundos. According to the central limit theorem, which of the following will happen to the distribution of the sample mean as sample size increases? Will the mean get larger? What happens to the mean? What happens to the mean for the distribution of the sample mean as the sample size increases? So look at these answers and think, what happens to the mean for the distribution of the sample mean as the sample size increases? What happens to the mean for the distribution of the samples? What happens to it? Well, you are correct. The distribution is going to get more normal. And what happens to the mean? You are correct, Kayla. Kayla, 100 points right there. You got it. Mean stays the same. Mean doesn't change. Because we're really good like doing every single way of knowing this. The mean doesn't change. So both of these are wrong. And then does it get less normal? No, it gets more normal. And we can view this visually again right here to see that this distribution up here is the original. And every blue dot down here is going to be one observation. Like this whole distribution down here of blue dots is the average of 25 observations. Like every single blue dot is 25 observations averaged together. Every single blue dot is 25 averaged together. And we make this distribution of doing it. I just did it 100 or like 400,000 times because I clicked it a whole bunch. Like this whole process right here was done 400,000 times. Really cool applet that shows how it works. And the new distribution is tighter and it's more normal. So the answer here is going to be it gets more normal. Sam, are you saying Sam got that hundo right there? I think Sam got a hundo on his quiz. So good job. We're getting those hundos. But that's got it. Let's head back to the main screen. Who's got questions? Let's see if we have time for another question. Might grab some lunch here real quick. What other questions do we have? We're going to get ready for class here in a moment. What other questions do we have? Let me know your questions. Sam, I'm glad we got this worked out. I'm going to cancel this. Glad, Sam, we got that worked out. So many things. Which one? What time is my class at? What time is my class at? Tomorrow, sorry. Right there, I was behind some stuff. Wait, Dr. Parano sees 201? We're online, so the classes are kind of in a different playlist. Okay, stuff right there. 250, yep. We're starting here in a little bit. So they're in different playlists, but I think we'll be live on Wednesday. What would people think if on Wednesday we just held the classes in a public stream? I'll knock over my glass. I'll announce that when is the office hour? When is the afternoon? There's no afternoon office hours today. We did a lot of campus content today. These are the office hours today. Here we'll go look at the schedule for tomorrow. Time for office hours. Here are the times of office hours. Here we go. Tara, good to see you here. Here's the office hours times. Are we doing the chapter 14 quiz or homework? We could probably take some time to do that today in class, Sam. Is that due? It's due tonight or tomorrow? I'm trying to think. I have so many due dates in my head. I've got just endless due dates of things. Awesome. Should we do one? We could do one of those questions now. We got enough time to do one more. Is there a question people want to do from chapter 14? I knock out my things every second. I literally knock out my little straws. Did a lot on the 21st. Yep. Lots of help right there. What questions do we have? We got enough time at least for one more if people want. We're just chilling out, relaxing, all cool. Playing some b-ball outside of school. Couple guys up to no good. They started making trouble in my neighborhood. I was in high school. I got in one little fight and my mom got scared. Said you're moving with your aunt and uncle in Bath, New York. Where I went. I didn't get in a fight though. Lived with my aunt and my uncle in Bath, New York. Upstate New York. What do we got question wise? Oh, decision trees. Let's do decision trees. Kayla, I'm so sorry. Kayla, let's hop here and do some decision trees. Do you want to do a categorical Y or quantitative Y, Kayla? Let's hop in and do decision tree. Here we go. Some horrible rapping right there, Tara. I have no fresh prints. Do you want to do a categorical or quantitative Y? Remember, decision trees can handle any sort of Y or X. Categorical, quantitative, it doesn't matter. Rock? We can put in either one. Okay, let's put in a categorical. Let's predict somebody's political beliefs. Ooh, getting controversial. So we're going to predict someone's political beliefs right here. And then we're going to put in all the X's except for political belief because that's not an X anymore. So let's predict people's political belief right here. Oh my gosh, I didn't do partition models. We're going to go here to predictive model partition, and then we're going to predict political belief. So let's go here, take every variable, drop it in here. Now we don't put in identifiers or things that act like identifiers. They're making a new Fresh Prince. Oh, I'm scared of that. I'm scared of that. There better be like a Jeffrey, and there better be. I don't know. I don't know. I'll see how it turns out. I'll judge it when it turns out, but I'm scared. I'd be like if they made a new Family Guy. What is like Steve Urkel going to be the dad? A new like Step by Step or new Full House? Well, okay, they did a new Full House. Okay, the number one thing in deciding someone's political beliefs is what? The number one factor, which you might say maybe that kind of makes sense. Which doesn't mean it's true for everybody. It's just trends in the data. It's just how the data do. This is real data once again. The number one thing for deciding someone's political belief, which doesn't mean it's true for everybody, is we ask people what? The first split right here is like the number one big deciding factor of the tree. We're trying to figure out people's political beliefs. There's three groups, mix of beliefs, liberal, conservative. So the number one thing right here is going to be what? Green or liberal? Go back and reorder. So the number one thing for deciding someone's political belief is, do you go to church? It doesn't mean if you go to church, yes, that you're conservative. You'd be more likely to be conservative. If you go to church, no, you're more likely to be a mix of belief or liberal. Liberal are the green right here. So now let's go split again. And we see here, do you smoke? So these are the people who, and we can try to make it bigger right here so it's easier to see. Oh, that's so interesting. If you go to church and you smoke, then you are liberal. Like you're more likely to be liberal. Like you just, if you go to church, if you want to find more, you want to find more liberal friends, go to church. Now there are conservatives who smoke and go to church, but if you go to church and you're like, hey, you're a liberal, right? You're like, how'd you know? You're like, you're at church and you're smoking. You have the highest probability of being liberal. This is Facebook friends right here. So we're seeing all this right here. I know it's weird, right? This is just how data do. Now this tree is not too amazing because this tree only explains about what % of the variation in someone's political beliefs. This tree only explains about what % of the variation in someone's political beliefs. This R squared right here is the % of variation in someone's political beliefs explained by the X's in the model. We're only explaining because we get this wrong a lot. Like you're like, oh, you go to church and you smoke, you're liberal, right? And they're like, no, I'm conservative. You're like, oh, well, whoops. My tree only explains what % of the variation in someone's political beliefs. That's the R squared right here. The R squared is how much we understand about the Y variable based on the variables in the tree. We only understand right about 10% of the variation in someone's political beliefs based on the X's in the tree. If I were to ask you, how many churchgoers are, let's say, liberal? How many churchgoers are liberal? That's the answer right there. What would you want to see if I said how many churchgoers are liberal? Great job, Kayla, right there. You'd say, Brian, can you show me this? How many churchgoers are liberal? Brian, please show me the blank. What do you want to see how many churchgoers are liberal? What would you like to see how many churchgoers are liberal? That we could then start to analyze it. If you want to see how many churchgoers are liberal, you say, Brian, can you show me this sort of report right here? That'll help me see for that group how many are liberal. What do you want me to add to this output to see how many churchgoers are liberal? We got religion and politics right here. Two things you never talk about. Statue of one. The leaf report. The leaf report right here. We're going to go to leaf report. And now we're interested in leaf number 1 and what? Go across the bottom. 1, 2, 3, 4. Which is the same thing here. 1, 2, 3, 4. 4 is a very tiny leaf if you can't tell. 16 people. Literally 16 dots. You can count them. You're interested in leaf what and leaf what to tell me how many church goers are liberal. These are people who answered, yes, I am a churchgoer. No, I am not a churchgoer. Yes, I smoke. No, I do not smoke. My Facebook friends are greater than or equal to 334. My Facebook friends are less than 334. Those are the way the questions are answered. So what for churchgoers, these are people in leafs what and what. The churchgoers are individuals in leafs what and what. The churchgoers are individuals in leafs what and what? They would be individuals. I'm going to use my draw on the screen option. They're individuals who are inside of leafs 3 and 4. Great job, Kayla, right there. So this is leaf 3, and this is leaf 4. I love that I can now draw on the screen. And this is leaf 1, 2, 3, and 4. So how many liberals are there? So how many liberals would there be, Kayla? We're interested in this right here, which is going to be the sum of that and the sum of that. So how many liberals are there in leafs 3 and 4? Well, sure. How many liberals are there in leafs 3 and 4? So the 20 is going to be in the bigger leaf. Did I do it right the first time? And then the 9 is going to be in the smaller leaf. 29. So what percent would that be if there's 29 total? So there's 29 total. Then what percent of churchgoers are liberal? What percent of churchgoers are liberal? If there's 29, then what percent of churchgoers... Oh, no, we're buffering. Hopefully that doesn't happen with the stream later. What percent of churchgoers are liberal? What percent of churchgoers are liberal? How would you mathematically find that? It should be like 8-ish, 9-ish percent. So how would we find what percent of the churchgoers are liberal? Like, we know that this is 29 right here because we added together these two numbers. That's where that came from. So how would we find out what percent of churchgoers are liberal? Which could be a different question. So of the churchgoers, 29 of them are liberal. How many churchgoers are there? There are 317. And that's the percent of churchgoers that are liberal. I think that's got it. Does that make sense there, everybody? Good stuff right there. I like that. I can now write on the screen. It's really nice. But that's got it. That's how we would use this. One other thing we could look at, I'll just mention it briefly right here, is the leaf report. Yep, Tara, you got it. Good practice on decision trees right here. Analyzing the output and understanding what these numbers mean and how to use them, and how these leaves down here are connected. Leaf 1, leaf 2, leaf 3, leaf 4, up to leaf 1, leaf 2, leaf 3, leaf 4, which is the same sort of, here, we'll make this go away again, which is the same sort of output up here. Leaf 1, leaf 2, leaf 3, leaf 4. Look at how leaf 4 is the little tiny one. Leaf 3 is the big one. Little tiny leaf and little big leaf right there. Big leaf. Little big planet, what we got. That's got it. And then the split history is going to show us the arc squared over each split, and it can tell us where to stop splitting the tree. So you can see here, it's not really increasing that much. So all that good stuff, but that's got it. Head back to the main screen. So the bottom left of the leaf has the total. Correct. Here, wait, let me see. Sorry, Kayla. This is the total right here. How many people on each leaf? That is correct there, Kayla. That is the amount 16, 301, 227, and 84 are inside those leaves. Like if you go up here and literally look at the dots right there, there would be 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 dots right there. Where's the total of all? 628. 628 is everybody. This is everybody all put together. Like if I were to prune this all up right here, pruning removes the bottom leaves. Everybody right here would be 628 total observations. And that's how many rows there are. Great answers, Tara, right there. 100 points. Keep it up. That's how many total rows there are in this data set. There's 628 total rows. And then we start to like subdivide down further when we split it apart. And we split this right here. The 628 are split apart into this. You always add up the bottom leaves like 311, 301, and 16 to get how many total there are. Like 628 would be the sum of 311, 301, and 16 because this is split into 301 and 16 right here. Is that making sense, Kayla and Tara right there? Good answers right there. Understanding hopefully how to read this output and what it means. Don't worry about the Gini coefficient, the G raised to the 2, and the log worth that deals with p-values. It's the log of the p-value, I believe, telling us if splits are statistically significant. We don't have to know that stuff, though. We don't know the Gini or the log worth. With that, ooh, so that one's really statistically significant. All right, there's the log worth for the split. Oh, the split below. Yeah, they're both statistically significant. I looked up what it meant one time. Awesome stuff. We'll head off right here. With that, we'll be back later. Going to be teaching here in just a minute or so, or 17 minutes. I'm going to go grab some food. I'll talk to everyone later. Bye for now, everyone. Bye. You got this. You got this. Just practice up. You got this. Bye for now, everyone. Bye. You got this, Kayla. Review.